Yeah.
Thanks a lot.
Thank you.
This is exactly the question that I wanted to ask. So I'm very happy that it came. We also have a few questions in Q&A, but unfortunately, since we're quite tight on time, we would have to move those as well to Gather Town. So thank you so much again for a fascinating talk. It was really awesome. And we're going to move to the next speaker, Anna Rosławska. Anna, are you ready to share your screen? I'm very sorry that I did not manage to read your affiliation, but I think that my extremely basic or even zero level of French would not allow me to. So Anna, the floor is yours.
Okay, great. Thank you very much for this kind introduction. So simply, I can say that I work in Strasbourg. In a team of physicists where we explore, where we use extreme microscopy to study the processes such as photosynthesis with individual molecules. So just to start, photosynthesis is a process that is really essential for the life on Earth. And in that process, we will have CO2 and water that are converted into oxygen and sugars. And all of that happens in plants when they're irradiated with radiation coming from the sun. And even though this process has been right now studied for more than 200 years, it's still not understood in its very, very detail. And one of the important aspects of photosynthesis is actually what happens right after the light has been absorbed. And it's really important that we understand this process as well, because we can learn from nature a lot. And in that way, we can optimize light harvesting devices in the future. And to do that, to study details of this process, we need to take a very close look into what happens in photosynthetic systems. And in very small scale, at the scale of individual unit that harvests light and performs the synthesis, we'll find structures like that. We'll have individual molecules in light harvesting complex, where each of these molecules is capable of absorbing light, of absorbing photons. And then these molecules will direct the energy coming from this radiation towards the reaction center, where actually the chemistry takes place. So all of these guys can be kind of thought as a fuel providing energy for doing this photosynthetic process here. And the structures, they are very, very small. And if we think of individual molecules, they're even smaller. And we are talking here about nanometer scales. And nanometer is a unit that describes, in fact, atomic spatial scales, such that in 1 nanometer, we can fit less than 10 atoms. So in our group, what we are really interested in is this process that is called resonant energy transfer. That is actually the way how the energy is moved from the place where it's being harvested towards the reaction center. And as we need to look at matter with very high precision, we employ a very special type of microscope that is called the scanning tunneling microscope, in short, STM, where we have our sample that we see here that we want to study, and we see that it consists of individual atoms. And to our sample, we bring very close a tip that is terminated with a single atom. And we bring them so close to each other that the distance between them is less than 1 nanometer. And in that situation, if we apply voltage between the two, we will observe quantum tunneling process. And this process leads to current that we can measure very far away from this structure. And because this tunneling current depends very strongly on the distance between the tip and the sample, if we raster scan our tip across the surface, we'll observe images like that, where each protrusion that we see here is actually an individual gold atom. And what is very important about this method is that it's not only microscopy, because as we have this tip that is very close to the system that we want to study, we may interact with it. And the first way in which we can interact with our system is that when we pass the tunneling current, in fact, we can actually generate light. And in that way, we can think of our system as an atomic scale light bulb. And this is actually a very powerful method because it enables us to do optical microscopy below the diffraction limit that usual microscopes are bound by. And we can really do it at the sub-nanometer scale. And here we profit from the fact that we have kind of an inverse photosynthesis process where we convert electrons to photons such that we can actually investigate very well what happens in between these two events. So to study the energy transfer, we use molecules that we see over here. They belong chemically to phthalocyanine family. And what is important about them is that they're chemically very close to the ones that we find in nature. For example, in chlorophyll, we see this core over here that is actually very similar to the core that we observe here. And because of that, these molecules are very nice because they bring us very close to natural systems. And then when we put them on our surface, we can image them and observe these nice shapes over here. And as we see here, each of these molecules is actually like a little bit more than 2 nanometers in diameter. And what we can do now, we can come with our tip to each of these molecules and pass the tunneling current through. And this will allow us to turn the molecule into our nanoscale light bulb. And here on the right, we see emission spectrum of each of these 3 molecules, where each one of them emits at a different energy, which simply means they have a different color. And we can use this emission as a kind of a sensor to see whether the energy has been transferred to that system. And STM has one more very important feature. Is actually, besides the imaging and exciting light, what we can do, we can interact with our system in a sense that we can assemble structures on the surface simply by bringing the tip very close to our molecule, such that the molecule will run away from the tip. And this is what we can do in our experiments. So here we see 3 molecules, and to observe energy transfer in our system, we need to bring them very close to each other. So we arrive with our tip here, we approach it, then we scan the surface again, and we see that this molecule has moved. Now we repeat the same procedure with the molecule that we see over here. And finally, we arrive with a very nice trimer where we can finally start to do some physics. And in that situation, what we can do, we can have the simplest possible trimer where we have 3 molecules of different energies, and we go to the molecule that has the highest energy. And now when we arrive to it, excited, and look at the light emitted by our system, we observe that first we can get some light out of the molecule that we directly probe, but also that the 2 neighboring molecules are emitting, meaning that we can successfully transfer the energy to one and then further to the other. And this is something very powerful because it allows us to play with the order of these molecules and the orientation and positioning. And for example, what we can very easily do, we can simply turn off the energy transfer if we simply remove a molecule. And in that way, we can study individual aspects of this energy transfer to learn how we can make it more and more optimal. And this brings me to the end of my talk. And I would like to thank all the people involved in the project and all our funding agencies. And in the end, I would like to summarize. So in my talk, I presented you how we can perform optics really at the atomic scale thanks to scanning tunneling microscope. We can also use it to build structures that allow us to simulate processes that are essential for photosynthesis, in particular the energy transfer that we can control and study in the very, very detail. Thank you for your attention.
Thank you very, very much for your talk, Anna. And if anyone would like to ask a question, please use the option to notify us, raise hand. You can also ask your question in Q&A or in the chat. There's actually one question on my side, because I'm a psychologist turned into neuroscientist. And if you'd have an opportunity to like summarize what you're doing in like a very plain, you know, a few sentences towards a person with a social sciences background, how would you do that? Is that possible?
Well, how I would summarize it very simply is that we go to the some kind of limit of matter in that sense. We explore the things that are in, like, we can reach atomic scale. So besides particle physics, you cannot go much deeper at the moment. So we really study the fundamentals of what is going on in the world at really the smallest possible scale.
Yeah, that's really cool, actually. That's really amazing. Thank you. And we have a question from Kuba Tomczak.
Yes. All right. First of all, amazing stuff. So I'm jealous even. I will ask one of these questions that always these old professors ask. So it's really fascinating. So is there some clear application area that you can really take advantage of your findings? Or I know that, to me at least, you seem to be rather theoretical person, right? Going really into the bottom of the world, right? But is it something like we can take advantage of your findings and apply it somewhere?
So, well, you're right. This research is obviously very fundamental, and applications do not come right away. But for example, one application one could imagine is, let's say, chemists synthesize some molecule that they cannot identify with the methods that they know. And because we can actually do optical spectroscopy at the level of one molecule, we can do experiments if there is, like, for example, let's say thousands of different molecules, we can address each one of them. And optical spectroscopy provides a fingerprint. So it allows us to identify actually what is the structure of the molecule. And that would be one way to actually apply our research to identify unknown products of chemical synthesis.
Wow, okay, I see. Thanks, really cool. Congrats.
We also have a question from Pavel. Pavel, you can talk now.
Okay, so I wanted to ask, thank you for the talk, really nice stuff. I wanted to ask about these shapes that you observe here. So these molecules look like flowers, more or less, here, right? With eight pieces around. And I wanted to ask for why is that, as the molecules on the molecular scale, which you were showing, they have this fourfold symmetry, right? So then another question I wanted to ask about is this Think PC, which on this image has a much different shape to the next images than you showed.
Okay, thanks. These are very, very nice questions. So as I mentioned, STM is based on probing the tunneling current. So it means that actually what we study is the electronic structure of our material, and the electronic structure that, in going a bit more detail, the orbitals of such a molecule do not exactly look like the backbone that we see here. And if we superimpose such a structure on top of a molecule, we will see, especially for these two guys, that the 8 lobes that we see here, they come in pairs, and each pair of them actually can be assigned to one of these chemical groups over here. And the core appears as this circle. There is another method that is called atomic force microscopy that actually enables to see bonds of such molecules. And coming to your second question, the reason why zinc PC actually looks a little bit different on the surface than the other two is that this molecule does move on the surface. So first, I didn't say it, but we work in very low temperatures, and our molecules are nearly fixed on the substrate such that they don't move, and we can probe them with that precision. But even though the zinc will turn a little bit one way and the other, and while we scan, we actually will observe somehow an averaged image of this motion. So that's why it looks a little bit different.
I see. Okay, all clear. Thank you.
I think that we also have time for one more question from Q&A. So one of them is, would it be possible to replicate photosynthesis outside of plants? Has it been done already? If not, would your research bring us closer to knowing how to approach it?
Well, as I said, this process has been studied for more than 200 years now, and I'm not quite sure that we can really replicate it from the very beginning till the end, if we can create something that we can call, like, if we can really create a leaf. But we can extract the compounds that take essential part in photosynthesis. For example, just taking this chlorophyll, and then it's possible to study just this molecule, put it together with other, forming these complexes. Light harvesting complexes can be studied individually. So there is a lot of research done on that. But as I said, still we cannot really, even if we can reproduce somehow the beginning and the end, so we come with a photon and we end up with an electron, physically speaking, we still cannot understand in detail the processes that take place in between.
Thank you very much.